I don't believe you did. So you got x1, y1, z1. What do you think happens when you use a dot product with 3? So, just like a two-dimensional dot product, three-dimensional is really easy. x1, x2 plus y1, y2 plus z1, z2. We did it with two dimensions. But three dimensions, it works exactly the same way as two dimensions. So, do you get out a vector or scalar? Yes, so for example, let's think we did 2, 3, negative 4, dotted with 1, 5, 1. What do you get? Two times 1, 2, 3 times 5, negative 4 times 1, so minus 4, 17 minus 4, 13. So, dot product, still easy. Still the same thing we did with the radio two dimensions. Now the cross product, that's a bit more difficult and a bit more time consuming. So a cross product, we start with two vectors, x1, y1, z1, same way, crossed with x2, y2, z2. So you've got dot product, this is a cross product. Yes. So we do a cross instead of a dot. Now, we get out this. y1, z2 minus z1, y2 times I. Is vector I? Is vector I? Minus x1, z2 minus z1, x2 times the vector j plus, let's see, x1, oops, sorry, these should not be vectors here. These are supposed to be parentheses. All the way down.
But the answer is going to be a vector.
Yes, the answer is going to be a vector. Some of them have to be I direction.
Why is it minus and you want?
We'll get to that in a second. There's going to be x1, y2 minus y1, x2 times v.
K.
Yeah. Or k, yes, nice. Okay.
Do you have to movement that?
No.
Why not?
Okay.
No.
How anybody wants to memorize it? Okay, so I need to remember to delete that off the test.
Okay.
However, does this look at all familiar? It should look a little bit familiar with something we did earlier.
Yeah.
Now, remember, plus minus plus.
Oh.
We had a plus, minus plus. Yes, dealing with matrices.
Woo!
So, this is the same as the determinant. So I, J, K are my vectors across the top. That's the first row of my matrix.
Wait. What is this? Do we have to do this?
X1, Y1, Z1, X2, Y2, Z2. So this right here is the same as saying we're taking the determinant of this matrix. Because remember, when we did the determinant, we took I, if we did it this method, we crossed out that and said I, the first number here, times the determinant here, Y1, Z1, Z2, minus y2 z1, and then we went over to the next one, do the same thing, so it's j times x1 z2, x2 z1 minus, and so on. That look familiar? So this is, because remember when we were doing the pattern, we did plus minus plus across the top.
Why are the I and J in the same there?
Because we get a vector out of it. And what is the I? What is the direction of vector I? Yeah, I is. You're remembering I equals 1, 0, 0. J equals 0, 1, 0, and K 0, 0, 1. So this is giving us a vector in a certain direction. Does that make sense? And they're going to remember how to do these. So we're going to do a couple of these. What was the alternate way of doing this problem? Anybody remember? Yeah. So let's do a problem. We've got a couple different ways of doing it. So it's a 2, 1, negative 3 crossed with negative 4, 2, 1. So 2 different ways of doing it. Remember, which way do you want to do it? Determinant or just using the big formula? Okay. So the first one that we're taking I times, I'm just putting I first so I don't forget it. What goes inside? 1 times 1 minus 2 times negative 3, or negative 3 times 2, remember it doesn't matter the order, minus j times 2 times 1 minus negative 3 times negative 4. So we did the first and the x and the z, and then we did the x and the z. Okay? Plus k times 2 times 2 minus 1 times negative 4. Okay, so 1 plus 6 is, so we got 7i minus, or let's see, we got 2 minus 12 negative 10, so plus 10j. And then 4 minus negative 4, so 8k. Right? Did I get it wrong? No. Okay. So 7i plus 10j minus plus 8k. So everybody's seems fairly easy. If we do the determinant method, no, it's the same. We set up the same way, so except for we're doing it across the top. I, j, k, and then 2, 1, negative 3, negative 4, 2, 1. And remember the two methods we had for doing this? Diagonal method, which was take the first two rows, rewrite them, I, 2, negative 4, j, 1, 2. So multiply down this way. So I times 1 times 1. There. This one plus j times negative 3 times negative 4 plus k times 2 times 2 minus negative 4 times 1 times k.
How are you factoring 7 and 10 and 8?
I'm just redoing the same problem, just using the determinant method of doing this. So I'm ignoring this. I should get the same answer, and then I'm doing this right now. This part.
But then when you're going to put it on 17.
So this part. So this is not part of this problem. This should be the answer of this problem. Okay. So basically, I started up here with these two things, and I did it once this way,
Yeah.
and I'm doing the same problem this way. So this right here, this part from here to here, generates this answer.
Oh,
Which
right.
means that if I do it this way, I should also get that answer.
Is that the final answer?
Yes, that should be a final answer. Like cross product. So now I'm just doing it in an alternate way to show that either way works.
You don't actually multiply it by the coordinates I and J and K.
Well, you could. For example, you could rewrite this if you wanted as 7, 10, 8. These two are they're equivalent in all ways. So if it asks for a component form, then you put this one. It depends on probably depends. I mean, most of the time it's gonna you're probably leaving it in this form because this is the form that you're generating it in.
Does it matter which way you put it?
No. That's why I'm doing it the second way. You don't have to do it the other way. So we have 2 times -3 times 5, and last one, 1 times 2 times j. Now if I did it right, you get the same answer either way. So I've got 1i plus 6i gives us 7i. Got 12j and minus 2j gives me 10j. Yeah. No, I'm just showing that you can do it either way. You get the same answer. I have 4k plus 4k. Okay. I must have made a mistake somewhere here. This is, oh, this is positive. Okay, that's a positive one. Never mind. So plus 8k. I was thinking it's a minus 1, which would have been a problem. So either way, you get the exact same answer. And it doesn't matter which one you use. Now, why might you use a cross product? That becomes an interesting question. Let me grab the meter stick.
Oh, yay!
So first of all, we're given 2 vectors in space. 2 vectors somewhere, right?
I see.
These are-
Right, yes.
Okay, so we've got 2 vectors that are some orientation, right? And remember, doesn't matter where they start, but if we started at the same point, we get some shape like this somewhere around. We don't know where it is, but it's somewhere. Okay? Now, is there a plane that goes through them? Oh, right here, the plane would go like this at an angle, right? If I did it over here, I still have a plane. Now, what the cross product does is give me a vector that is perpendicular to this plane. If this plane is here, this one might be generating this vector. Or it could be generating this vector, but it wouldn't. Remember, the point doesn't matter. Because remember, they don't have position. When we're talking about vectors, we aren't talking about a position. They're a direction with a magnitude. So these 2 vectors are theoretically, they could be something like this. However, because they're vectors, it doesn't matter where they start.
So where could that be?
Wherever we want. This point is arbitrary, completely arbitrary.
But you kept that vector on the point.
Yeah. Well, this vector, I mean, it could be somewhere out here. However, this point right here is completely arbitrary.
Does it have testing vectors?
Okay, I'm not sure you're following this. This point does not matter. This vector could be anywhere. Its positioning does not matter. Because vectors do not have a position. This vector here is the same as the vector here. These are exact same vectors. No matter where I put it, this vector is the same, because vectors do not have a position that they're starting at. I mean, it could be up here. It could be out here. It doesn't matter. Position does not matter for vectors. But it's orientation and length. So it is always going to be perpendicular. So that's just convenient to put it right here. So we've got a plane right here by these two. This one, when you do the cross product, you get something perpendicular to it. Perpendicular plane. Now, how would you test orthogonality with three vectors? Or not three vectors. Two three-dimensional vectors. What do you think? Same way. Which was? If the dot product equals 0, the two vectors are orthogonal. Works in 2 space, works in 3 space.